Welcome back, Quadrature fans. My name is Marian Elena, and today we will tackle the relationship between tangent, slope, and area. And this is something when I took calculus, and believe it or not, I actually took calculus in college. That was kind of a weak spot in my education, you could call. I really didn't understand that relationship, particularly on the integral. I could follow the derivative, but totally misunderstood the integral. Today we'll have an interesting take. You already have seen a relationship between areas and slopes last time. Well, let's see. What did we have? I mean, look at this. Here's an example of a relationship. Look, it's this area, basically x to the n plus 1 times k sub n. And the slope, tangent slope, is x to the n minus 1 times c sub n. One raises by 1 degree, one lowers by 1 degree, multiplied by appropriate invariant. Already we're seeing sort of a relationship right there. These are box operators. They're all... So today we'll look at it from another angle, and so let's go to it. No doubt you've seen this diagram sort of before. We have y equals x to the n. I drew it actually for y equals x squared. You got 4 to this, but I'm trying to make it implement it for x to the n, general purpose. These are ordinary curves. That's what we're dealing with in quadrature. Nothing else, just ordinary curves. Okay, so our setup is now 0 to a. So if it's x is x to the n, we're going to have a to the n over here, right? That makes sense. Okay. And, we look around and we're trying to get this estimate. Remember the time when I first began these videos? I did an estimate, and I estimated something on the upper bound. That would be our diagonal. This area, that would be the upper bound, and then the tangent right here, that would be the lower bound. So we can see that the area underneath this wedge, right, that's what we're after. Okay, well, that's going to be estimated something between the lower bound and the upper bound. And tell me where you think I should stop, right? I would say right about there, huh? That's a good place to stop. So let's stop there. Okay. Perfect. All right. And that's kind of an approach that, not too little, not too big, but just right. That's the Goldilocks principle, right? There's Goldilocks and the 3 bears, and she figured this out back in 1640. She knew it. Smart girl, huh? All right. So that's Goldilocks. So, okay, we're going to say, all right, that's going to be, well, it's going to be, let's just draw it. Bingo! Whee! See that? Okay. So there's our estimate of where we think our area is. Kind of midpoint, somewhere in between. So let's tackle that. Let's just call this distance from here to here C. Okay, that's this distance. And we got A over here, A squared. So what Goldilocks found is that this happens when you take the average slope, the average between the diagonal and the tangent. You see that? That's kind of halfway, middle way. The average slope. We don't want this slope because that's too much area. We don't want the tangent slope, too little area. We want just right. The average slope. Goldilocks knew it. All right. So let's set it up. Slope, typically we say mavg equals, well, we know that the tangent is simply n times, well, you got rise a to the n divided by run. A times n. That gives you this tangent line right here. We've been doing this in the past videos. This is our c to the n, our invariant. Okay? So you know about this. So that's rise over n. That's this diagonal times n. That gives you the tangent. Well, plus the diagonal itself is a to the n over a. And the whole thing is over 2 because it's the average, right? That's what we're after. That gives you this average slope. Okay, let's see what happens when we do that. Well, let's just solve that, or just collect it. Basically, we get n plus 1 over 2 times a to the n over a. All right, nothing to it. But this average slope, the slope of this blue line over here, well, that also equals the rise over the run, right, of this. So that equals, what's the rise? That's a to the n divided by the run, which in our case is c. So c mavg. So these two are equal, right? So a to the n over c is equal to this whole thing, right? Equals n plus 1 over 2 times a to the n over a. See that? These two are equal. We're saying that, okay, well, a to the n, we can cancel that out. We're basically going to solve for c. That one cancels out. What does c equal? Well, we just have to invert it, and we got it, right? Pretty simple. C equals 2a over n plus 1. Think it's true? Yeah, that's it. All right, so we got C. All right, now let's look at the area of this triangle here. What is that? That's simply, well, base times height, or height times base times 1/2. So area and that's the area of this blue triangle, which we're saying it closely estimates the area of this wedge. You see how closely? If you take some of this area and transfer it over here, well, guess what? You're going to have a complete filled-in triangle like this. Transfer this little piece of area into here. Imagine doing that using some kind of Cavalier's trickery, but whatever it takes. But that's what we're doing. Okay, so we're just estimating. We said C, and Goldilocks said, well, that happens to be the point where these are average. Okay, so let's crank it. Let's see what happens. Area equals, well, that equals 1/2 times base, height, a to the n times your base, c. That's triangle, right? But c is over here, so, okay, that equals 1/2 times a to the n times 2a over n plus 1. Ah, look at this. 2 cancels 2. And what do we get? We get area equals a to the n plus 1 over n plus 1. Area, and guess what? That's exactly what we found out over here, right? K sub n times x to the n plus 1. That's our finding. So it matches. You get, this is Cavalieri's formula, by the way. And so you see off the bat that, if you have the average slope, that gives you this nice blue triangle. That area is exactly Cavalieri's formula for this curve, x to the n. Beautiful relationship. So you see how they are related. If you have one, you have the other. And notice, this is for any x to the n. It could be x squared, x third, etc. So there you have it. A simple proof. Credit goes to... There we go. So, all right. So we'll sign off. And before there was calculus,
there was quadrature.
Here.